part of the LC2 fam. Welcome everyone. It's a distinct pleasure to introduce Ron Shen from the University of California, Berkeley, who's one of the pioneers of using nonlinear optics to understand the crystals and surface interactions, which we appreciate. And we also are appreciative of metamaterials, and Ron is going to tell us about optics of metamaterials this morning.
Good morning. Let me first thank the organizers.
Yeah, maybe you can use the lapel mic.
Oh, this one, yeah. Okay. Thank the organizers for inviting me, and I would also like to thank you for coming to this talk so early instead of watching the opening ceremony of Olympics. I'm going to just give a very brief introduction on optics of metamaterials. As you know, that metamaterials have attracted a great deal of attention recently, just because in optics it can give you a lot of interesting, unexpected phenomena. So our work is actually a teamwork supported by DARPA, and we collaborated with Hewlett-Packard and also other people at UC Berkeley. And Hewlett-Packard made the materials. They have tremendous capability of making nano-meter structures using imprint method, so that you can have mass production and later on if it works. So the people that are in the team, SY1 is our representative, and we do the optical characterization, and Wei Wu and you at Hewlett-Packard make the materials, and then also Catalina and Alexander made the calculations, the numerical calculations. So I'm going to just first give you some review on the basics, and then give you a case study that we did on the so-called Fishnet structure. Tell you the fabrication and the optical characterization. Then we have both linear and nonlinear characterization of the network. And the dynamics is because we're interested in optical switching and modulation. So by definition, the metamaterials are artificial materials, optical materials. And they are composite materials composed of structural units that are much smaller than optical wavelengths or smaller than wavelengths, so that they could appear homogeneous to the incoming wave. The structure can be designed to give you materials that have optical responses that do not exist in nature, and that's the interesting part. Examples of, you can get refractive index less than 0, of course it's effective refractive index. And in that case, this is the most studied case, because with negative refractive index, you can get all sort of strange optical phenomena. And n equal to 1, of course, means that light can just go through and you don't see the object. And that's the very hot topic of crowding. The structure unit of the metamaterial is defined as to be much smaller than the optical wavelengths, or then if it's away than the wavelengths. And they can be treated or considered as either atoms or molecules. So an optical field coming in will induce an electric dipole sort of locally on the structure, and magnetic dipole on the unit, just like inducing dipole on the molecules or atoms. So we have also the electric porosity and magnetic porosity. In fact, more generally, you should have considered also point dipole and other higher order dipoles. Higher order molecules. But most people just ignore those. We should say that the point dipole is generally as large as magnetic dipole. It should be considered. So here we just talk about the electric dipole and the magnetic dipole, and therefore the electric porosity and magnetic porosity will characterize the optical response of each structure unit. Then you can imagine the low density of those structure units will give you a medium that's gas-like, and a high density of such units will give you a condensed metal. Example on the structure unit is if you have a metal sphere. Usually these metamaterials are made of metals, especially silvers, because of the small size. And in the case of a metal sphere, if you go to Leonard-Lipschitz book on electrodynamics in continuous media, you'll find this expression for the electric dipole induced on the sphere and the magnetic dipole on the sphere. And then for the cylinder, you also have those expressions. And then you talk about the split ring, because you would like to have a resonance. And Smith and Pendry, they imagine to have the split rings. And split rings will give you a resonance for the porosity in the magnetic sense. The reason is you have the magnetic flux penetrating these loops, the holes, and the gaps here and also between the rings will give you the capacitance. So you have both inductance and capacitance that give you the LC resonance, just like the ordinary circuit. And in those descriptions, we always just talk about so-called quasi-static limit, in the sense that the optical field can be treated almost like a static field, except there's a frequency. So that means even in the optical frequency range, if this structure is small enough, then you can still talk about an LC circuit resonance with this resonant frequency. And then if you have an ensemble of such structures, it will give you the metamaterials with the magnetic resonance, like that. The red part is the absorption. The real part is the dispersion. So if you then consider, then you see that in the high frequency part, mu is negative. Okay? So that gives you the negative mu, and then then if you add to each ring, each split rings, a metal wire, then the metal wire gives you the plasma resonance. The plasma resonance, of course, is the plasma response. The plasma response is omega p is the plasma resonance frequency, and we have this usual expression. And you can see that if omega is smaller than omega p, epsilon will become less than 0, or even less than 1. And you can see in that case, the metamaterial will have both negative dielectric constant and negative magnetic permeability. And that is what we are interested in for the negative refractive index materials. So what the negative index materials will give you? Well, we know that the wave vector is given by E cross B, the direction. Okay? But the pointing vector is given by B cross H. So if you consider that B and H are in opposite direction because mu is less than 0, then you will have S and K in opposite direction. So in other words, the phase velocity and the pointing vector are in opposite directions. And that, you can say, epsilon less than 0, mu less than 0 will give you a refractive index that is less than 0. And that leads to S parallel to minus K. But actually, this is probably the more correct definition for this negative index materials to give you all these interesting phenomena. So starting from that, you can show everything that characterizes the negative refractive index materials. So the most striking effect is, of course, the negative refractive index or negative refraction. And as you can see, if it's a positive refraction material, you will get the normal Snell's law. The beam refracted going this way, this pointing vector and K vector are in the same direction. But if it's negative refractive index, if you just try to match the boundary conditions for K going in the opposite direction of this energy flow, you can see in order to match the wave vector at the boundary, that beam has to come in this direction. So it shows the refracting is negative. Okay. So you can see that for starting from S being opposite to the wave vector, you can explain this negative refraction. Because usually, when you take A equal to square root of epsilon and mu, you can have plus minus. And it's up to you to define which is plus, which is minus. So the potential applications, I just want to show a few. The most famous one is the so-called super lens. And as you can see, now with the negative refraction, we don't need a curved lens. It can be a slab. And that slab naturally will give you the image point outside the material. On the other hand, this negative refractive index material has another very strange effect, that is the focusing of the imaging can be below the diffraction limit. As we all know, that the diffraction limit is the limit of the ordinary lens system. Here, we said the diffraction limit means that the object cannot, the image cannot resolve delta x, which is given by 2 pi over kx, and this k, 2 pi over k is of the order of wavelength. In other words, if I have delta x object here, it will give out the k vectors in all directions, but we will have some k vectors larger than omega over c, or larger than 2 pi over lambda. Okay? And those waves, of course, cannot propagate because it will be, the e to the ikx will become negative. So this kx propagating with a magnitude larger than the wave vector 2 pi over lambda actually will not be able to propagate because there is a very strong attenuation. So in other words, those radiation will not be able to propagate from here to here unless this particular slab has some kind of amplification to compensate the attenuation. And that is actually the property of this negative refractive index materials. And What we therefore can get, if this amplification exists, then we can expect that the resolution will be beyond the diffraction limit, just because some of those light that are not supposed to propagate can actually propagate to the image point. And this is don't worry about the equation. What we actually have is suppose the color is not clear. We're supposed to have a three-layer system. A three-layer system is 1, 2, 3 layer. Okay. So the three-layer system, the middle layer is from here to here. Okay. It's supposed to be the yellow color. And therefore, this transmission coefficient is just the three-layer equation that everyone knows. Bobby Pearl, laser cavity, thin film, interferometer, all those belong to this equation. Okay. And with this equation, and you put in the condition that this middle layer, the slab, has epsilon equal to -1, mu equal to -1, then the refractive index is equal to -1, and the outside is there is air, and it's equal to 1. Then you can show that this coefficient, transmission coefficient, actually has an exponential growth. Okay. So that exponential growth is going to compensate the attenuation of the so-called evanescent wave. And that then allows those waves that cannot propagate from the object to the image start to appear at the image point. And therefore, the resolution can become much better. So this, in a way, has been demonstrated. And as you can see, here is it's a nanometer structure of the order of 100 nanometer resolution, and this is the STM picture, and this is for AFM picture, and this is the superlens image, and this is I still limit the K factor a little bit, and so it's not as quick. So this is the super lens, super resolution application, and that was actually a big activity going on. DARPA, for example, is very, very interested in this phenomenon and try to see whether they can make the actual materials to work. If we have this slab as super lens, then you can imagine you can send light through optical fiber, and this will be then the object points. And through the super lens, you will be able to connect the image points, and this will be the optical fibers again. Then you can have a photon link from here to here. Okay, and you can propagate on. But then if you suddenly change the refractive index here, for example, from negative refractive index to positive refractive index, then of course the link is completely cut off. And that induced delta N, of course, can be done optically or electrically. The optically can be very fast, and that gives you the fast optical switching and modulation. And that's a more sort of useful system that people can build. You can have the optical fiber coming in, and outside it starts to diffract. And as it diffracts, it will distribute the power over this entire panel. And that entire panel is the superlens. And then you can see it will refocus By doing so, you will have no nonlinear optical effects because the power has been redistributed over a big area and the intensity becomes small. On the other hand, you can also modulate, put in a weak RF input, and that will modulate this delta N here. And after the modulation, of course, you will have essentially the optical switching or modulation of the output through the induced delta N, and the output then has a strong modulation of RF on it. So that's a way to transmit a strong RF power signal. So that's, again, has some special uses for maybe military purposes. We can make a laser easily, a ring laser easily. We just combine the negative index and positive index section-wise. So now the question is, if I give you a negative index materials, how would you recognize it? Now, of course, you can say, I just do the negative refraction measurement, and that's very clear. Unfortunately, these days, we cannot make a very thick negative refractive index material because of fabrication problem. So usually it's a very thin, and when it's a very thin film, you'll never be able to see the negative refraction so clearly. So then the question is, how do you know it is a negative refractive index materials? That means you have to measure the refractive index or measure epsilon and mu. So that's the linear optical characterization of the material. And again, it should be, in principle, it's trivial because for optics, if you know the linear optical transmission and refraction, in principle, you can measure all the properties. Right? So that's exactly what it is. You deduce from the measurement, this is what you want to do, either the permittivity and permeability, or you want to deduce refractive index and the so-called impedance. And all these quantities are complex quantities. Both real and imaginary parts are there. So you need form measurements. And clearly, if you do transmission and refraction measurements, you get intensity measurements, and these are two quantities, but you also need the phases, and that gives you another two quantities. So you can measure transmission, refraction, intensity, and the phases, and that will then determine the four quantities you want. And again, that's just equations, three-layer problem, and you have T and R. And if you can measure the complex transmission and refraction coefficients, then in principle you can deduce the refractive index from Kn here, and the impedance from also the transmission and refraction. And then that gives you epsilon and mu. And as I said, we're interested in optical modulation. And there we're talking about inducing a delta N optically. And that will hopefully be sufficiently large so that you can easily see the optical switching effect and fast. And then we also are interested in the nonlinear optical characterization of the materials. Now, the earliest demonstration of such materials is the split rings and the wire. So now, here you suppose you do a transmission measurement. And if I don't have this wire, then as you remember, mu is less than 0 at the magnetic resonance or near the magnetic resonance. So if mu is less than 0, but epsilon is larger than 0, then of course the refractive index becomes imaginary. If the refractive index is imaginary, then the wave is a decaying wave, and it will attenuate instead of propagating. So you see, therefore, in this frequency range, we have mu less than 0. And therefore, without this ring, we have the mu less than 0 in this range. So the transmission has a dip, because it's an attenuated wave. Now, at this ring arm, or this wire, without this wire or with the wire, we now have epsilon less than 0 because of plasma resonance, but plasma response. And you can see suddenly the transmission has a peak, so that inverts the transmission from from refraction to transmission. And this is a direct demonstration of negative refraction. If you have the ordinary wedge made of Teflon, this is all microwave studies. Okay? So you have a microwave coming in, and you get the positive refraction out. As you see, this is the wave out. Okay? And if it's a negative index materials, it comes in, and now it refracts that way. If you plot it out intensity-wise, the Teflon case does not depend on frequency. They all have positive refraction. But for the negative index materials, only in this frequency range, it has the negative refraction. So that demonstrates directly there is a negative refractive effect. But for application, we're really interested in negative index materials in the near infrared to the visible range. Near infrared because we have the optical communication window, and particularly 1.55 micron. And in the visible range, of course, everyone would like to see a negative refraction by eye. And you can see the viewing image and so on. So therefore, the real interesting range for negative index material is in the near infrared and visible range. So here I'm going to give you this case study. We start by talking about how to make the negative index materials in the optical range, and then we talk about characterization. So the way this so-called nano-imprint lithography method is essentially the same as ordinary lithography method or imprint lithography method, except that it's in the nanometer scale. So what you do is you first have to make a mold. Okay. So here is the blue one is the mold. It's going to print. Okay. So what you do is first coat a substrate with a transfer layer and a liquid polymer resist layer, and then you press on it by the mold, and you get this pattern. So after the imprint, then you can etch it all the way down to the substrate, and then you can evaporate what layers you want. So in the Fishnet case, you evaporate 3 layers: silver, silicon dioxide and then silver. And after the evaporation, you see this kind of structure, and then you can etch it again and lift off what you don't want, that part. Okay? And so what's left is then this structure. So with this, you can imagine it's possible to do mass production. You just print, you do the stamp. So with this method, we can make this kind of pattern that's also a negative index material. We do the fishnet, and it has 3 layers: silver, silicon, silver. Unfortunately, it's difficult to make it the top surface and bottom surface same area, because evaporation always has shadowing effect. But it still works, and as you can see from the electron microscopy picture, it indeed has the nanometer scale. And this is the product. And now, where does the negative index come from? Okay? It has to have a magnetic flux of a linking loop, so that you can have a negative resonance that gives you the negative mu. And then you also should have the so-called plasma response. So here is where you can see where this the magnetic resonance comes from. Imagine you have the incoming field with electric field in this direction, okay, and a magnetic field in this direction. Okay. So this bar here is this bar. Then you can see in the cross section, you will have this current loop, although here is the displacement current. But this forms a current loop, and that links the magnetic flux, and therefore that will give you the so-called magnetic resonance. The capacitance, of course, coming from that gap. And on the other hand, this magnetic resonance will then give you this mu less than 0 at a higher, slightly higher side of the magnetic resonance. And then you also have the field linking these wires, and the electric field are parallel to these wires. That will give you the plasma response. So in that case, the epsilon less than 0, and give you n equal less than 0. So what do you get? This is probably clearer. You can imagine that fishnet structure can be decomposed into these squares and bars. Okay. Bars are these bars, and squares are the leftover squares in the crossing area. And these crossing area, each one looks like a magnetic structure that gives you the negative mu, and the bars give you the plasma resonance. So combined together, you have the fishnet, and that gives you the magnetic resonance, the real part like this, and here you have the negative mu, and the bars will give you the plasma resonance, as you can see, plasma response, as you can see above the plasma, below the plasma frequency, you have negative epsilon. And the red ones, the red curves are the loss curves. So with this fishnet structure, you can do the numerical calculation to figure out what is the transmission of this layer and the reflectance of this layer. And then from that, you can deduce the real A and imaginary A. And this is done by Katrina at Lithography, and you can see that indeed we will get a negative index in this region. which is close to the magnetic resonance. So then we need to do experiment to show whether this is indeed the case, whether we indeed can get negative refractive index. And for the measurement, imagine, of course it's straightforward because it's a linear optical measurement. The only thing to worry about is the sample is extremely small. It takes some effort to have a mode that's 500 times 100 micron. And so it's still tiny. And therefore we need to use laser to do this kind of measurements. And for that, because we want to do spectroscopy, we need a tunable laser. And because we want to do optical switching modulation, we need pulse lasers, femtosecond and picosecond lasers. And for modulation, we also need to induce sufficiently large delta N. Therefore, we need a high intensity pulse. And so here is one of the setup. We just use a picosecond YAG lasers that pump the optical parametric system that allow us to tune from 0.4 to 50 microns, so that covers the whole range easily. And this is the geometry that we're going to characterize the material. And we need a phase measurement, and you can do either interferometer type of phase measurement, or here we're just looking at the anisotropy of the phase. So here are the results of the measurements. You can see from the transmission, the black curve, and the reflectance, the red curve, we indeed see some kind of resonance structure. So let me explain a little bit. Here is some near the magnetic resonance. And below this, we still have mu larger than 0. Okay. But the plasma resonance already, plasma frequency is here somewhere. Okay. So we above and below that plasma frequency, we will have epsilon less than 0. But in this region, mu is larger than 0. So again, the refractive index is imaginary. If the refractive index is imaginary, the wave is at an attenuated wave. It's not a propagating wave. So the wave gets attenuated in this region. But then, somewhere here, starting here, you have mu less than 0 because of the magnetic resonance. And now we have epsilon less than 0 and mu less than 0, and the wave becomes propagating slowly. So that's why the transmission starts to rise again. So this is the theoretical calculation. It matches sort of pretty well. And the phase measurements, again, for the transmission, for the refraction and transmission curve. So from those measurements, the transmission and refraction coefficients, then we should be able to deduce the refractive index. And here is the refractive index, and you can see that 0 is here. So from in this particular range, the refractive index is negative. And then we want to see whether we can tune this magnetic resonance. And that would be nice, because especially if you can just turn the knob and change the resonant frequency. So of course, in order to tune the frequency, you have to change the refractive index. And it's hard to change the refractive index of the metals, but it's easier to change the refractive index of the dielectric medium sandwich between the metal layers. So here is the other reason we want to change the frequency is we want to design the metamaterial so that the resonant frequency or the negative refractive index region is around 1.55 micron, the optical transmission window and the optical communication window. So here they just change the parameter, the dimensions, and then here, for example, you have 39 nanometer and 35 nanometer, and obviously for the silicon dioxide, and obviously the frequency can change accordingly. So by doing so, changing the thickness of the silver or the silicon dioxide, we can actually tune the frequency to 1.55 micron. And here you see one is 1.6 micron, the other is 1.55 micron. And so we now get the material to the frequency double volts. And then we did the measurements, and indeed again, here you see only epsilon less than 0 in this region, and in this region epsilon less than 0 and mu less than 0. So the transmission rises again. And here's the phase measurements correspondingly. But I mean, again, we can use real N and imaginary N, and you can see again for refractive index N, 0 is here, so in this whole region around 1.5 micron is all negative. So the next thing is we want to have a larger refractive index change by optical pumping. Now silicon dioxide, we all know, is transparent. It's very hard to change its refractive index. So we have to change the dielectric medium accordingly. And the one case is put a semiconductor in between. And silicon is the easiest thing for the electronic industry to do. So you have to put the amorphous silicon layer in between. So with that, again, the same pattern for the fishnet structure and so on, except that the dimension is slightly different, and that still gives us a resonance around 1.6 micron, 1.7. So this is the calculation, and the measurement again shows this dip in the transmission. Again, remember that the drop here is because epsilon less than 0, mu larger than 0. The rise here is because epsilon less than 0, mu less than 0. So the phase measurement is here, and from this we can again reduce refractive index, and again you see that in this whole region the refractive index N is less than 0. So with this, we are pretty sure that we do have a negative refractive index material. The only problem is how to make this material thicker. It would be, this is almost just two-dimensional. What we really want is a three-dimensional structure so that you can see those effects much more easily. So the next thing is to see whether we can indeed get optical modulation. And now with silicon in between, we can easily excite the carriers in silicon. And with the carrier excitation, the refractive index of silicon is going to change. And if the change is strong enough, we should be able to see the modulation. We should be able to see the change in transmission. So with this structure, what we do is, as you can imagine, we just use a palm beam exciting this metamaterial, and then a probe beam to probe the change of the refractive index. So that's the palm probe experiment. I think everyone knows well. So we use this tunable infrared as a probe to probe the resonance region. And the pump is this 532 nanometer beam. It's the picosecond pulse system. And with that, you can see that for different fluids, pump fluids on the sample, we can see this transmission curve changes. Okay. And also the frequency changes, the resonant frequency or the bit frequency changes. And as a function of the energy or the fluence, we actually can see transmittance change is not linear. And so this is just to be a little bit more quantitative, and you can see with pump and without pump, the phase changes, and the transmittance changes, the reflectance changes, and therefore we can deduce how much refractive index changes. And so you see the refractive index, the real part of the refractive index, changes from minus 2.5 to something like minus 1.5. So that's a fairly big change, although we have not really optimized everything. We can change the pump frequency to make the excitation more efficient, or even better, we should change the silicon into something else that's more effective. So the question is, where does this refractive index change come from? And of course, it's coming from excitation of the amorphous silicon. And here we do the dynamics measurements as a function of the probe delay. You can see that after the excitation, it decays away. And that decay away is because of the carrier relaxation in the silicon. And why do I say that? Because the red curve is the time-resolved measurement on Fishnet. The black curve is the induced absorption on a film of amorphous silicon only. And so you can see the induced absorption in the amorphous silicon has the same decay curve, more or less the same decay curve as the Fishnet. So it indicates the mechanism is indeed the carrier excitation and relaxation. So we use this simple exponential decay expression to fit the curve, and the solid curve fit very well. So it says that the relaxation time is about 58 picoseconds. Now, this is to also find the refractive index change is reasonable, and I'm not going to bother you with that. Indeed, at least semi-quantitatively, the agreement is good. Now, actually, we recently made the femtosecond measurements and found this response time or the relaxation time can be even shorter. Because here we use a 20 picosecond laser pulse to do the experiment, what we found is this kind of relaxation, the time scale is of the order of tens of picoseconds. And now with femtosecond, 100 femtosecond pulses, we actually saw a 1 picosecond peak relaxation, which of course cannot be seen here because it's sort of integrated out. And so we're still trying to figure out whether this very, very fast modulation can be effective in changing the transmission. So what we can see is indeed we can get fairly strong modulation on the refractive index. From minus 0.214 to minus 1.45, indeed this is a fairly large change, and it can shift the transmission quite a lot, especially if the medium can be thicker. And the mechanism, as I already said, is coming from the carrier excitation in the amorphous silicon. And the possible improvement I already mentioned, we can replace the amorphous silicon by materials with large nonlinear coefficient. This is, in fact, it's already known to some extent, because another very popular field in quantum electronics is the terahertz generation, terahertz spectroscopy. And for terahertz spectroscopy, one way to generate the terahertz is a transmission line with a gap. And that gap, you can shine a pulse laser, a laser pulse on it, and stop the conduction. And then after the laser pulse is over, it will relaxes. And so the conduction exists only for a very, very short time. And the shorter the better, because then the current pulse can emit, can really give you the terahertz. So for that scheme, you need high response. Okay. Equivalent to large delta N. High response and fast response. Fast is equivalent to our fast population. So if we can just pick their materials, probably it will work. So the nonlinear optics part is also quite interesting, because although metals are absorbent, they also are highly nonlinear. Therefore, if you make those nanostructures out of metals, those nanostructures can all be very highly nonlinear. Okay. In addition, we are talking about resonances, magnetic resonance and so on. It's all coming from the metal structure. But if you think carefully, the resonances are all so-called plasma resonances of the nanostructures. So if you have a sphere, you have the plasma resonance of the sphere. If you have a ring, you have the plasma resonance of the ring. And when we talk about plasma resonance, we can imagine we're talking about the so-called optical wave, optical field, converted into a so-called polar field. That means waves interacting with the material, in that case interacting with the plasma. And so the so-called plasma resonance actually will give you a very, very strong local field at the resonance. So at resonance you have very strong local field, and the strong local field is going to give you very strong nonlinear optical effect. So that's the whole idea, that the nonlinear effect in metamaterials can be very, very strong and can be very interesting. So here is what the idea I just talked about, and hopefully if we indeed can make those nonlinear, those metamaterials very easily, we can have new nonlinear optical materials, especially those that we want to integrate in your optoelectronics integration. So here we can, for the Fishnet, again, Fishnet structure that we just described over and over again, we can see second harmonic generation from the Fishnet easily. Here, for example, the black curve, or the flat curve here, okay, the flat, is coming from a thin film of metal, thin film of silver. And by symmetry, for S polarized in, S polarized out, or P polarized in, S polarized out, you will have no second harmonic generation by symmetry. But for our case, you can see the resonance at the magnetic resonance. Then for these polarizations, the thin film silver can still give you some second harmonic generation, but you see no resonance. But for the fishnet structure, you can see the resonance. And you can see the third harmonic generation easily. Again, you can see the resonance, resonant enhancement at the magnetic resonance. And the more interesting thing is if you compare those resonance peaks, you will find in all these cases omega is at resonance. Okay? Now you see 3 omega is sharper than 2 omega, 2 omega is sharper than omega. Also, if we do four-way mixing, 3 omega is sharper than 2 omega plus omega, 2 omega 1 plus omega 2, and then sharper than omega 1 plus 2 omega 2. Okay. So it says, although you have only one resonance, only omega 1 is our resonance, somehow the 3 omega sees a much higher resonant effect. Now, I started by saying that these nanostructures can be considered as atoms or molecules. If you think that way, then you would say, if I have an atom or molecule, I have all these energy states. Okay? And if I have, maybe I just go through that. So if I have all these states. So if I have omega 1 on resonance, then all the other excitation will not be on resonance. So I have only a single resonance, right? So whether it's second harmonic generation, or third harmonic generation, or wave mixing, I only have one resonance. Right? I don't have double resonance in the molecular case or atomic case. But in our case, it seems to suggest that the 3 omega third harmonic generation, I have triple resonance. That's why it becomes sharper. Now, why is that the case? Well, it's all because the resonance is in local field, not like in the molecular case on states or energy transitions. So what we have is, for the nonlinear effect, the signal is coming from the induced polarization square. The induced polarization is proportional to the susceptibility of the material. In our case, the susceptibility of the material is mainly coming from metals, and the metal has no resonance by itself. But then we have the local field. The local field here. That's the Lorentz factor, the local field factor. The local field here, and we can see the local field gives you the plasma resonance. So if I have 3 omega generation, then I have 3 local field factors, and all these 3 local field factors have resonance. And that's why it gets so much more enhanced. And this talks about a very interesting concept. That is, although we can sort of treat the structure units of metamaterials as atoms or molecules, but that's only true in the linear optical sense. But if you're talking about nonlinear optics, the two are different. Well, I think I'm going to end just by giving you something to think about. This, as you probably already heard, by Pendrey's idea, you can make cracking, and this has excited a lot of interest, especially in the young people, after they have seen the Harry Potter movies. And then here we talk about negative index materials, And you can think about this if you have a short pulse. And if you have this short pulse propagating in that material, you have energy goes in this direction, wave goes that direction. How could it happen? Right? Energy goes that way, wave goes that way, and they separate it out. Okay. So physical intuition becomes very difficult. But if you're interested, you can read this paper to give you some idea how to answer this question. So let me just very quickly talk about the prospect. We have the metamaterials that can give you new materials that's non-existent in nature, and therefore it has the potential to revolutionize the field of optics. But what we really need is 3D metamaterials, and that's very difficult to fabricate. The other problem is we use metals, so optical loss is extremely strong, and if we cannot sort of compensate the loss or eliminate the loss, we will be in trouble in applications. And so people use the idea of compensate the loss by gain. But in any case, we need a breakthrough in fabrication. And tunable metamaterials are really desirable. And we also, of course, appreciate experimental studies on the 3D metamaterials in the optical range. Thank you very much.
Thank you very much. Since this is a workshop and we don't have parallel sessions, I think it's important to call for questions here. After Ron will be very happy to answer. Yeah, Bob.
This is perhaps a basic question, but it's always bothered me, so maybe you can help me understand. In the super lens, as the evanescent field propagates towards the lens, that evanescent decay is energy going back that's being reflected. So when you get the super lens, and now you say that the evanescent wave is getting amplification, that seems like that's actual energy gain. Where is it coming from?
Well, it's just like the tunneling, optical tunneling. You don't really have the energy gain. It's just that the field redistributes in the whole system. So you don't say, because the evanescent wave cannot propagate. If it cannot propagate, it cannot carry energy. So it's really just, at the beginning, it will start to, there is a transient period for this field to redistribute. So during that very short period, you don't have the so-called evanescent wave or negative refractive index. It just tries to adjust the field distribution. And once it establishes the field distribution, it basically says, this is the field pattern for that particular system. So it's very similar to the optical tunneling case, and that's always difficult to explain to the students.
So in all of these materials, because of the need to have a higher density of units, you are on a lattice of some kind that you showed as rectangular lattice. And when you got to the point where you're explaining these resonance narrowing in the nonlinear case, I was expecting to see some influence of the local field caused by the induced fields or the combined effect of the surrounding lattice such that you had some kind of Lorentz factor due to that. But you seem to be explaining it more with the higher order local field that didn't involve the lattice somehow. That is. So to what extent is that?
No, I mean, we're talking about essentially a condensed metal.
Right.
Okay. It doesn't have to be a lattice or regular structure. It could be like an amorphous materials, right? Randomly arranged, as long as it's condensed metal. Okay. With condensed metal, each unit I mean, there will be strong interaction between units. Okay. And they will influence each other's resonance. Right? So the resonance we show is the resonance of the whole unit. And then when you come in with the field, just like ordinary material, you have the local field. Okay. The local field, of course, is influenced by the layers. And in the metamaterial case, it just happens that we also have plasma resonance. At the plasma resonance, the local field effect is particularly strong. In fact, in those structures, the local field can be separated into two parts. One part has no resonance, the other part has resonance. And it's the resonant part that gives you this strong effect in the nonlinear phenomena.
We have a question from Ron.
So there's a remote question from Liquid Crystal Institute at Kent. Very interesting talk. We would like to know more about where the nonlinear effect comes from in the fishnet structures, from the metal or dielectric materials between top and bottom layers.
Yeah. Well, I just mentioned, we have this nonlinear susceptibility chi. That is mainly from the metal. Okay, because actually that particular experiment is done on silicon dioxide. That's the dielectric medium in between. And silicon dioxide is known to have very, very small nonlinearity. So the nonlinearity is mainly, in this case, coming from the metal part. And then through the surface plasma resonance, we get additional resonance enhancement at the magnetic resonance. Okay. Now, it's possible to also have a dielectric medium, which is highly nonlinear. For example, if I put in gallium arsenide as the in-between layer, then it's possible that the nonlinearity we see will be much higher. Okay. Because this chi will not be also coming from the gallium arsenide. And the other thing is, you're coming from the Liquid Crystal Institute, and you see, we want to have tunable resonance. So it would be nice if you have liquid crystal as the dielectric medium. Then you can apply the field on the metal part, and you can change the dielectric constant by just turning it on.
So, that's a basic question. When we look at the diffraction limit of light, we normally divide it into the So when we look at the diffraction limit of light, a very good way to derive it is using the uncertainty principle. How do you reconcile the idea of perfect lensing with the Heisenberg uncertainty principle with the idea of close one leaving and arriving at exactly the...
I was using the Heisenberg principle, but I didn't say it.
It violates, because the way you're deriving the diffraction you're right, you're going beyond that, and I'm just wondering how you...
Right. The Heisenberg uncertainty principle in this case is delta kx times delta x is about 1. So it cannot be less than 1. Right? So that's the diffraction limit I also mentioned, right? So the reason that was the limit is because it's a wave nature. Delta k, delta x has to be equal to 1. I mean, it's less than, larger than 1. Okay. But now we're talking about having evanescent wave. The evanescent wave is usually not the propagating wave. Heisenberg uncertainty principle refers to the propagating wave. Okay. So this is how we can bypass the Heisenberg uncertainty principle. So the key point is the propagating wave.
Okay, well, more questions? Okay, well,